Hi everyone, the question right now says us that we need to find the maximum of all the K sliding windows that we have in the array. And a naive approach of solving this question would be like, let's say if I have whatever is the length of K, we can um we can find the maximum of that using, if we use a nested loop, we can go big of n into k time complexity, or if we use priority queue or heap data structure, then we could go using max heap, we could go n into log k complexity. How would we implement a brute force approach? um See, the brute force approach, let's say we have this array. So they in every iteration there will be two things. An element will come, so there will be an incoming element and there will be an outgoing element, correct? So when an outgoing element is not the maximum element, it's fine. Whatever is the maximum element, we'll just compare that with the minimum element, and that will be the maximum element for a particular sub array or a sliding window for that particular window. But what happens if the leaving element, or let's say was the maximum element, let's say in this case 3, 1 and minus 3. So if this was a maximum element, we now have lost the maximum element for the remaining array. So then we would have to iterate through every, based on our implementation, we would have to check the remaining k numbers. So that is not a very good approach because we have lost the history. We don't know the second largest number or the third largest number, whatever. And given the constraints, which is like num short length is less than or equal to 10 to the power 5, this approach n into k or n into log of k would cause a TLE. So now what we do is we can use a doubly ended cube for this, which would be monotonic in nature, which is strictly decreasing. So how do we do that? And why do we do that is the question. So let's say we have this array, fine. So let's take this example. This is our array. So let's say this is our window that we are looking at currently, case 3, right? So now we are using, how do we go about this is, let's say we are currently, like, there will be an incoming element, right? So if incoming element is there is the logic. I mean, let's first get into the core intuition. Let's say we have this window, okay? And there's an incoming element. Now, let's say if I had a window of 1, 2, 3, okay? And 4 was coming in it, and k is 3. So, tell me one thing, that now whatever window that we have, it would include 4. Matlab 4 would live longer than the element to its left, right? And we also know that if 4 is larger than the rest of the elements to its left, then the elements to its left can be discarded. Why? Because since we're finding the maximum element, so 4 is the maximum, and every window that 1, 2, 3 is a part of, 4 will also be a part of from here on, if we talk about it. So then we discard all of the smaller elements and then we place 4. This was one thing. Now there can also be one thing when we are iterating. Let's say we had these 4, 3, 2 was there in our, Deque. Now let's say I encounter another element, let's say 1, or let's say 5, or let's say 3. Okay. Now there is one thing. Is 4 all currently our maximum element? No, it is not. Why? Because the length of k is 3 and 4 has fallen beyond that. So 4 has expired. So then we need to discard 4 as well. So that is what we are doing. So the core intuition that I'm talking about says that if like let's say I have an index I and I have an index j and I is less than j. So if my nums of I is less than nums of j, I can discard I or nums of I because nums of j would be there in the remaining windows now, because every time we are adding an element, so every time a new number will be incoming. So this is our core intuition, and then we always check for expired elements as well. So the first thing was we check for expired elements and remove them, and the second thing is we keep the DQ monotonic or strictly decreasing. So how do we do this? So let's see, we check for the expired element and remove them. So let's say if, let's say I have a start index and I have an end index. So end minus start plus 1 will give me the number of elements, right? Here the number of elements is k. So if let's say I am standing at I, which is I. So now to find what's the start. So is equal to k. So now S comes out to be I plus 1 minus k. You know, so this is my start index. So any index smaller than this, if start index is smaller than I plus 1 minus k, that index has expired. So chop it off the list. So this is the formula that we came up. And the second thing is, if we keep, we have to keep the Q strictly decreasing. So the thing I'm trying to say here is, like, let's say if my Q has 1, 2, 3, 4, sorry, it will be strictly decreasing. So 4, 3, 3, not 3, 2. So again, I get 3. So then I know that before I add 3 to the end of the queue, I need to remove the smaller elements. Why? Because now going on, I will have like let's say if there is a window in which 3 is a part of and 2 is a part of, it means 3 will also be a part of it. Since we already have the maximum, we never need 3 and 2. So we'll remove this. So the logic here that we used was, if, like, let's say whatever is there at last, dq dot get last or offer pole, wait, get last is equal to, I mean, if this was a function, so if this was the case and those elements were smaller than the incoming number or equal to as well, so then we can discard them. So this was the logic we used, right? Now let's see, why did we use DQ? See, there are 4 things that we need to do. We need to add elements to the end, right? Add incoming elements to the end. Then we need to add, remove elements at the end if they are smaller than the incoming elements. Incoming element. Now third is our first element will be maximum for the current window. Current window. So we have to get from the first side as well. And then we also remove expired elements from the end. From the first. So from the front. So now you see that a started stack or DQ won't work here. Why? Because we are adding and removing from the start and back of the data structure. So that's why we have used a doubly ended queue here. So this was the entire intuition and approach that we are going to take. And we'll just get started with the coding part. So firstly, we are going to see the return type of this is integer array, right? So let's say result is equal to new int. What's the size of the array? So let's say we have, n. Let's say my int n is num.len. So the size of array will be n minus k plus 1 number of windows, since it is inclusive. Now what do we do is, now we have to initialize a DQ. So let's say DQ, DQ of integer, and DQ is equal to new array DQ. So now what we do is that we are going to store indexes here. Why? Because we also have to calculate the expired indexes. So that's why. So now let's start a for loop. But before that, in the end, we have to return result. Fine. Yeah. So now let's start a loop for int I equal to 0. I is less than n, I plus plus. We'll iterate through every element of nums. And then what we'll do is, so what are we going to do is that if we are going to check if the numbers at the front have expired. This is my first step. So how do I check if the numbers at the front have expired? So firstly, I have to check if DQ dot is empty. So if it is not empty, only then can we check if the elements have not expired. And let's say my DQ dot peak first will give me the first element in my DQ, and it will give me an index. So if nums of this, sorry, if no, not here. So if this will give me the index, and if this index, you remember, is less than this, I plus 1 minus k, then I know that my index has expired. So then what do I need to do? I need to pull from the first part. So then I'll do dq dot pull, which side? First side. So this is the logic here. Now, now that I have checked at the end, now I have to keep checking. Now I have to add the incoming element. But before that, I need to check if elements are smaller than the incoming element. So then I'll write a while loop. While the first case will be if Q is not empty. After that, we are going to check, and this time we'll get from the back. So dq dot peak last, and we'll get an index. So we'll check if nums of dq dot peak last, if this is smaller or less than equal to my incoming number, which is nums of I. Nums is the length of the array, right? The name of the array. Yeah. If this is the case, we are going to peak from poll from last. So poll last. Now we have the perfect DQ. So then we'll offer into the DQ, the current number that we have. Offer which side? Last side. And what do I need to add? I, the index. So now then what I do, I check. And then I need to also store the result in my result array, right? But I can't store my result in the result array if I don't have my first window. So I'll check if my I is greater than equal to k minus 1. Only then have we got a first window complete. So we'll do result of R index, and we will peek from first. So DQ dot peek first. And R index, let's initialize it to 0. And yeah, this was the code. Let's run this. 7 0 0 0 0. We'll see what is happening. So yeah, the thing here is that we haven't done R++. So that is the problem that we have. Because after adding here, we should have incremented. So now here we have some issue again. Let's see what's the error. Okay, now we are adding the integer index value here. Rather, we should have added the number at this index. So yeah, now coming to the time and space complexity of this optimized solution, our time complexity is big O of n. However, we see a while loop nested inside the for loop, but the overall time complexity is linear. Why? Because any element can be added into the queue DQ once and be removed from the DQ at max once. And that is the reason why we have time complexity as big O of n. And what about my space complexity? Um, See, we have this results length array. Let's ignore this requirement. Let's say we are not asked to calculate this. So then we have this DQ, and at max it will store k numbers. So that's why our space complexity is big O of. So yeah, that was it from my end. Thanks for watching. Bye.